Hello everyone and welcome back to Introduction to Number Theory. In this video we will continue proving the Weyl's theorem, and once again we will deal with grasshopper whose step will be equal to beta. Well, you might remember that when we stated the Weyl's theorem, the step of a grasshopper was equal to alpha. Well, of course, it doesn't matter which letter you use to denote the step of grasshopper. However, I use beta because we will use beta for a grasshopper with step alpha. And this beta we use here will be small. It should be sufficiently small. We don't know yet why we need a sufficiently small beta, but you might have a clue. Okay, however, this grasshopper is jumping along a circle which starts here and ends at the same point. And on this circle we have an interval. We denoted it by I. And we're concerned with the frequency of the grasshopper getting into this interval. So let's denote by m the number of steps inside the interval, and denote by n the number of steps on the circle. So the grasshopper makes n steps and moves, and among these n moves he got into the interval m times, and the frequency in this case is equal to m over n, and we wish to estimate this frequency. Well, m consists of getting into the interval on all of the loops of the grasshopper. So grasshopper starts from some point. This is not necessarily the starting point of a circle. Starts from some point and jumps and jumps and jumps, and on his first loop enters the interval several times. Denote this number of times by I0. Zero is the number of the loop. And on the second loop, the grasshopper enters the interval, well, I'll write it this way, IL, where L is the number of the loop. So I1, I2, I3, first loop, second loop, third loop, and so on. And separately, I will denote the number of enterings, the interval on the last loop among first n steps, because you understand that the first loop is not complete. So the grasshopper did not start from the beginning, and on the last loop the grasshopper will not end at the end of the circle. So let's suppose that there are L complete circles, and L plus first is incomplete, so denote it as I with index L plus 1 prime. Okay, so what about n? Of course, n also consists of the number of marked points on the loop of beginning plus complete loops and plus the last one, which could also be incomplete. Well, it could be complete, but we don't know that. We don't know that, so we need a special notation for the last loop. And we know that for every complete loop, so for every L such that it's greater or equal than 1 and less or equal than L, we know that IL over CL is between, let me write it here, the length of the interval minus b over 1 plus b, not b, beta, it doesn't matter. We don't have b's here, so b will be beta. And it's less than length of I plus beta over 1 minus beta. These are inequalities that we proved on the previous video. Okay, but having this, we should somehow estimate that fraction. So let's go from these inequalities to inequalities containing sums of I and C. Well, obviously, I, each of them, is less than this fraction. I'll just write it completely, multiplied by C, the corresponding C, of course, and greater than that fraction multiplied by the same C. And this holds for every L, for every loop L, which is complete. So we can sum all these inequalities, add all these inequalities to one another, and we will gain that sum of i's from 1 to L capital is less than, well, the same fraction Of course, I'm rather lazy to write these fractions so frequently, but what can I do? But here we have, of course, sum of c's from L equal to 1 to L. And on the left-hand side, also the sum of c's from L equal to 1 to L multiplied by the same fraction. But these inequalities are something connecting merely such sums. Which are not entirely m and n. So we know something about these expressions. But what about incomplete loops? What can we do with them? Well, the answer is simple. Since we're talking about the limit where n tends to infinity, we can write the following inequalities, n over m over n. Well, it is equal to this over this. We can change the sum of i's, this, using inequalities here. Change, I mean substitute. So we can say that it is greater than something plus something else plus, well, I really don't have enough space to write it completely, but I'll denote it symbolically, multiplied by sum of c's, where, well, I suppose you understand that minus in the numerator and plus in the denominator denotes, namely, this fraction. And this fraction in the numerator will be plus, and in the denominator will be minus. So over here we will have fraction plus here minus here multiplied by sum of c's. And we divide all this by c0 plus cl plus 1 prime plus just sum of c's. And the same here. I'll just copy. Well, can we say that this fraction here is actually greater than I, length of I minus beta over 1 plus beta? Well, no, because there are some numbers in the numerator and the denominator, some summand that can ruin this inequality. But since we're talking about large n, because n tends to infinity, we can state that if the number of loops, if L is big enough, then this sum will be so big that not this equality holds, not this inequality holds, but inequality where we subtract from this fraction a small number gamma, small positive number gamma. And the same with the right-hand side, this fraction will be less than plus gamma. So we need to understand that these inequalities hold not every time, but for all sufficiently large L. This means that there is a number of loops after which these inequalities hold. Where gamma, well, what is gamma? Gamma is a small positive number which can be chosen in front. This means that I give you gamma and you give me the number of loops, starting of which these inequalities hold. So finally, let's make a conclusion. We see that m over n is less than and greater than which holds for given in front gamma and sufficiently large number of loops. Let's memorize this because we will need it in the next video where we will finish the proof of Weyl's theorem.